Hello and welcome to this module on passive WDM components. We will continue the discussion of isolator. In the earlier module we have looked at isolator, which is polarization dependent, but clearly I cannot use a polarization dependent isolator because I do not know what the input polarization will be. So, the simple thing that you can think of would be to actually use two polarization dependent isolators. The big idea is that I do not know what is the input polarization, but I can assume that this can be represented in terms of its horizontal and vertical polarizations, correct. I can always break up any incoming polarized light into its horizontal and vertical polarized light. So, I put one Faraday isolator for the horizontal polarized light, one for the vertical polarized light, and that would be my polarization independent isolator. Let us look at the construction of that. So, we start with arbitrary polarized light, which I can represent in this particular way. You have to remember that this means that the input polarization can be expressed as linear combination of horizontal and vertical. Then we use what is called as a polarization beam splitter, which is a device which separates the incoming polarization into its vertical and horizontal polarizers. This can be implemented by a crystal, especially a birefringence crystal or a prism, okay. And once you have separated them into vertical and horizontal polarizers, so you can put in a Faraday rotator. So, let us say we have a 45-degree Faraday rotator for both arms. So, I have a similar 45-degree polarizer. So, the after Faraday rotation, the polarization state will be rotated by 45 degrees. So, this would be the polarization state. Next, I put in a 90-degree plate or what is called as a lambda by 2 plate. A lambda by 2 plate will change my 45-degree linear polarization into a horizontal polarization here. Similarly, if I put in one more lambda by 2 plate, okay, this is another 90 plate. So, which means that the angle again will be rotated by 45 degrees. Okay. So, I put in here the angle gets rotated and 45 degree this way polarized light will become a vertically polarized light now. So, I have a horizontal and a vertical, but I can use what is called as a polarization beam combiner, which will work exactly in the opposite way, right. It will combine a horizontal and a vertical polarized light into a single polarized beam. It contains both horizontal and vertical polarized light. So, this is a simple polarization independent operation. Of course, if you try and trace what happens from the other side. So, let us say you start with this in general polarized light, this has to be converted into horizontal and vertical. So, you get horizontal and vertical here and at the output of the 90-degree plate. So, this is how you get the conversion, and what happens at this point is that this 90-degree plate will rotate in a counterclockwise direction, right. So, it will then change from horizontal to this 45-degree plate, this will again change in the counterclockwise direction in this way, right. Now, Faraday rotator is a device which is non-reciprocal. It does not care which way your input signal is coming in because it will always rotate clockwise by 45 degrees. This is a 45-degree rotator. So, this will become horizontal now, right, and this will become vertical because after clockwise rotation this would become vertical, this would become horizontal. Now, this horizontal is going into the vertical arm and vertical is going to the horizontal arm, which means the polarization beam splitter will not combine them. So, PBS or PBC are reciprocal devices. They can split an incoming polarization into horizontal and vertical. They can also combine in horizontal and vertical into a single linear polarized light. Okay. So, this is how a polarization independent isolator works. One of the major uses of polarization independent isolator is in protecting the optical devices, especially you want to protect a laser. So, you put a laser and then put an isolator, so that if I have any other optical element that might reflect some light, that reflected light will not be reaching the laser and causing instabilities in the laser operation. Of course, sometimes you want to create necessarily some instabilities in the laser, but that is a different point. You normally want to avoid any signal being reflected back into the laser otherwise it will simply damage the laser. Okay. So, anywhere wherever you want to put some isolation, you can put a isolator. Let us consider this very interesting setup. Okay. So, here I put what is called as an optical amplifier in the form of a fiber, which is called as a erbium doped fiber, and I pump this erbium doped fiber. We will talk about what this means in when we talk about active WDM components. Okay. So, this is an optical amplifier. Now, I somehow want to create unidirectional propagation, that is, I want my signals to propagate only clockwise. What I do is I simply put a isolator here which will carry signals only in this way, because any reflection will be filtered out by the isolator. So, this is essentially where isolators are extremely useful. We will now go to one of the most useful devices called as wavelength filters. A wavelength filter is a very simple device. Suppose I have a wavelength filter which is designed for filtering lambda 1, which means that I might come in with a set of spectra which has lambda 1, lambda 2, lambda 3 and lambda 4. At the output what I get is lambda 2, at the output I get only lambda 1, because that is the one which is selected by this wavelength filter, and all these other wavelengths lambda 2, lambda 3 and lambda 4 are reflected. Now, if you do not want them to go back to the source, right, you can put a circulator, right. So, you can actually send signals through a circulator, so that when a group of wavelengths come in to the wavelength filter, which is a lambda 1 wavelength selection, then lambda 1 will go out, whereas onto this port 3 of the circulator you will get lambda 2, lambda 3 and lambda 4. Therefore, they are not going back into the original direction and giving rise to some crosstalk. You can, so this is called as a wavelength filter. Okay. You can also find what is called as a multiplexer in market. What is a multiplexer for a WDM system? A multiplexer is a very interesting device. It takes in signals of different wavelengths. So, let us say these are at wavelengths lambda 1, lambda 2, lambda 3 and lambda 4, and then combines them into the single output called as the COM output or the common output. Okay. It does so by having multiple, sorry it is not very nicely drawn, but please excuse my figure problems, but this is lambda 1, lambda 2, lambda 3 and lambda 4. So, it actually combines signals from lambda 1, lambda 2, lambda 3 and lambda 4 and then passes all of these signals onto the common port. So, this is the multiplexing operation. In order to create good multiplexers, you have to create nice spectral pass bands. Okay. You have a pass band and the width of this pass band is normally determined by 1 dB bandwidth, that is to say you look at 2 wavelengths at which point the power would have dropped from to 1 dB of the maximum value, and that would be the pass bandwidth. Of course, the traditional way of talking about the bandwidth is to talk about 3 dB bandwidth. 1 dB gives you the flatness of the filter bandwidth, whereas 3 dB is the more common way of specifying the bandwidth. You can also see here that a portion of the signal goes into the second region, right. So, this is causing what is called as the crosstalk, that is, if I have a signal at lambda 1, a portion of the energy at lambda 1 goes into lambda 2. Because lambda 2 is adjacent to lambda 1, this is called as adjacent channel crosstalk. Okay, assuming that these are all different channels, then this is called as adjacent channel crosstalk. Okay. Sometimes you will also see what is the non-adjacent channel crosstalk. Okay. Non-adjacent channels are those which do not lie, they are not besides each other, they are lying far away from each other. Finally, these filters or multiplexers also have what is called as an insertion loss. So, this is the amount of insertion loss for a typical multiplexer. This insertion loss will be anywhere about 0.5 to 1 dB, okay. Sometimes slightly more than that, but 1 dB is a very typical insertion loss. These skirts which you can see, right. So, you can see here these are the skirts of the pass band. These skirts, if they are quite long, right. So, for example, I might have a hypothetical filter which has this kind of a skirt, right. This is bad for me because it means that there is a significant amount of crosstalk into the neighboring channels. The goal of multiplexers would be to try and make this passband skirt, in fact for the filters also, to make the passband skirts as narrow as possible. One other problem that actually occurs with filters is that if I consider the same wavelength filter but I cascade them, as and when something that happens when you are looking at a long distance transmission, at each span just before the inline optical amplifier you will put an optical filter in order to limit the amount of noise entering into that particular wavelength. So, overall if you see over say 10 or 20 spans of propagation, there are about 20 filters, and if you now look at the overall response of the filters, the overall response would have narrowed down. So, it might actually cut down some of the input signal spectrum. In order to avoid this problem, you have to have a flat response, and this flatness of the response is measured by the 1 dB bandwidth of the filter. Okay. So, this is one of the things that you will have to take care when you are looking at system design for a N-span optical communication system. Alright. So, we will now look at some technologies which are used to implement multiplexers and demultiplexers. Demultiplexers do the exact operation, do the exact opposite of the multiplexing operation. Okay. So, we will look at some techniques which can be used for implementing these wavelength filters and multiplexers. All these techniques can be thought of as based on one simple idea. Although idea is simple, in practice they are quite difficult. The idea is that when two waves come in, okay, so let us call this as waves E1 and E2 of typically the same frequency, they can interfere, okay, interfere constructively or destructively. If they interfere constructively, intensity will be maximum here. If they interfere destructively, then the intensity will be minimum here. Okay. So, this simple phenomenon of constructive and destructive interferences is the basis of many wavelength filters. Wavelength filters can be classified into types which based on the physical principle involved. Gratings are typically diffraction based ones, okay, and you have what are called as etalons. Etalons consist of a cavity, constructive and destructive interferences of waves inside the cavity, and then you have coupler or MZI based devices, that is Mach Zehnder interferometer based devices, which is implemented by putting two couplers and a path length difference between the two. We have already covered this last one, so I am not going to talk about that. In the previous module we have covered this. So, we will look at gratings. Etalons again are kind of little difficult to talk about, to derive the equations it is little tedious. So, we will not derive equations for this, but I will give you the final results which you can use for designing the Fabry-Perot etalons, Fabry-Perot etalons being the most popular type of etalons. Okay. You all are familiar with a grating idea, right? What is a grating idea? You know that if I take two slits, right, if they are separated by certain distance and then I send in light, assume that light is coming off from a far away region, so that it essentially approaches it as a plane wave. Okay. So, we will also assume that the slit width is very small, the slit width is this fellow is very small here. Okay. Light can come in at certain angles, and these rays which are coming in are essentially making an angle of theta I. Okay. So, these are making an angle of theta I, and then from here they will diffract with an angle of theta d. This angle is measured, both rays of course will diffract with the same angle because they are coming in with the same incident angle theta I. The distance between the two slits is what is called as the pitch of the grating. Okay. P is what I denote as pitch of the grating, theta d is the diffraction angle. Again, as these rays propagate, okay, they are essentially parallel to each other, then they will interfere at what is called as the image plane. Okay. So, they will interfere at the image plane. Now, what is the result of this interference at the image plane? Well, look at this, they are essentially parallel because we are assuming that image plane is quite far away and the slit width is very small, that is the slit width W is very small compared to the pitch P, which itself is compared very small compared to the wavelength that I am sending in. Okay. The pitch itself is very small compared to the wavelength. Because we are looking at wavelengths of 1.5 micron propagation, right, this is the 1550 nanometer window, the pitch is typically about 1/10 of this. So, it is about 0.15 micron. The slit width W is about 1 order magnitude less than this 0.15 micron, which would be about 0.015 micron or very nearly in the nanometer range. Okay. So, what is the result of this interference of these two waves? Well, in order to find out the result of the interference, you have to find out what is the angle over which the extra propagation is happening, correct. So, this angle is distance over which extra propagation is happening. This extra propagation comes by looking at this one. So, this is the extra distance for the diffracted wave and this is the extra distance for the incident wave, right. We know that the extra distance here can be written in terms of angle theta d. This is theta d. So, this angle will be 90 minus theta d and this is the hypotenuse for this triangle. So, you have p into sine theta d, because this would be cos of 90 minus theta into p will be equal to the adjacent side over here, correct. So, this is coming from, or delta d, this is coming from the out diffracted light and this is the input condition. Similarly, for the incident case you have p sine theta I must be equal to delta I. The total path length difference is of course the sum of delta d and delta I, right. We will call this as PLD. PLD is delta d minus delta I or delta I minus delta d, it does not really matter. Okay. So, this path length difference, when you multiply this one by the propagation constant, will be equal to the total phase shift that you are going to obtain. Okay. So, if I assume that the propagation constant is 2 pi by lambda and this is the lambda for which I am designing this grating, then the overall phase shift can be either 2m pi for constructive interference or it can be an odd multiple of pi, so that you get a destructive interference. Suppose I consider constructive interference, then I can remove this 2 pi on both sides and write down what is delta d minus delta I, that is actually p into sin theta I minus sin theta d also, does not really matter here. Okay. Time, so this must be equal to m into lambda. This equation is called as the grating equation. Okay. If you look at typical construction, there will not be only two such slits, there will be multiple slits. Okay. So, these are all the multiple slits and this P is the pitch of the grating. Okay. The slit widths are almost neglected. Light comes in here. If you have two wavelengths lambda 1 and lambda 2, then you will have one diffraction for lambda 1 with at an angle of theta d1. Okay. So, this would be for theta d1. At a different angle, which is theta d2, the light for lambda 2 will be diffracted. Okay. So, this would be there on the image plane. This is called as a transmission grating. Sometimes you will also look at what is called as reflective gratings. So, they will be reflected at two different angles. So, that is called as a reflective grating. One interesting way in which you can create a grating is what is called as fiber Bragg grating, or in general a Bragg grating. Okay. You are familiar with this Bragg grating phenomenon from your X-ray diffraction study, in case you have done so, right. So, you would take two planes and then imagine light falling in here. One light comes in, gets reflected, then the light penetrates to the second, after the first interface, hits the second interface, comes back, right. It's the second, this one, the electron goes to the second lattice plane, hits the second lattice plane, comes back and then comes up again. So, these two will then be interfering with each other. They might again interfere constructively or destructively. Okay. A similar effect can be obtained if you consider two counter propagating waves, okay, of propagation constants beta 1 and beta 2. For this case, the effective propagation constant difference beta 1 minus beta 2, if this would be the propagation difference and if they are propagating in a region which has a certain length lambda, okay, or a certain periodicity lambda, this would be the overall phase change. Remember, propagation constant times distance is the phase change, right. If this phase change is equal to some 2 m pi, then they will interfere constructively. Okay. For the same wavelength beta 1 will be equal to beta 2, they are just propagating in the opposite direction. For the wavelength lambda 0, the propagation constant is beta 0 and beta 2 will be equal to minus beta 0, because beta 2 is in magnitude equal to beta 1, but in phase is equal to 180 degrees. So, this is equal to 2 beta 0. So, you substitute that into the equation, you get 2 m pi. Let us take m is equal to 1 as our solution. Okay. Then you replace beta 0 by lambda. Of course, the actual propagation constant has to be written in terms of the effective refractive index, okay, because this effective refractive index will be the effective refractive index over this entire region. Okay. So, you get 2 into 2 pi by lambda n effective is equal to 2 pi cancels on both sides, 2 n effective into lambda. This capital lambda is the periodicity, this must be equal to lambda. Okay. This is called as the Bragg grating equation. Okay. So, this is the Bragg grating equation, and in a fiber you can create what is called as a fiber Bragg grating. Okay. Fiber Bragg grating basically comes by creating the index difference inside the core. So, you can create an index difference like this. So, you have a high index, low index, high index, low index. Okay. How can I obtain this? I can actually take two interfering UV beams, okay, and because the core of the optical fiber contains certain photosensitive materials, if you dope the core with germanium in order to increase the refractive index, it is extremely photosensitive to UV light. So, when you send in two UV lights which are interfering with each other, there will be regions of, they are interfering, therefore, there will be regions of maxima minima, right. So, wherever you get a maxima, there will be a increase in the refractive index, wherever it is not, it would be a decrease in the refractive index. In fact, it would be a gradual decrease. Okay. You can also create these fiber Bragg gratings by using face masks. Okay. You can do those face masks, and only those regions which are exposed will be higher index, those which are not exposed will be of lower index, or the other way around, does not really matter which way it goes. The net effect is that the refractive index in the core is now a function of the distance, okay, which then couples the counter propagating waves. Okay. So, as the wave propagates, there will be a reflection, and then it will create a partial wave into the second medium. Let us look at it. Suppose I consider this as the high low refractive index. Okay. So, this is the high refractive index region, low refractive index, high and low. This is the period of the grating, correct. So, this is my period of the grating. Let us assume that I come in with certain wave, this is air for now, okay. For this is a simple way of understanding what Bragg grating does. So, as this wave comes in, because it sees a different refractive index, there will be a reflection. But remember, you are going from lower refractive index to higher refractive index, which means that there will be a 180 degree phase shift upon reflection, right. So, this reflected wave has picked up a 180 degree phase shift. Then this wave goes into the second medium, then it accumulates a certain phase shift, depends on the length of this high index region. Okay. If I tailor the length of the high index region such that the phase shift will be 90 degrees, then it will accumulate a 90 degree phase shift. When you go from H to L region, there will be reflection, but there will not be any phase shift picked up by the light. Okay. However, while propagation there will be another 90 degree phase shift, then this light will come out into the second region, right, with an overall phase shift of 180 degree with respect to the incident wave. Okay. This is the incident wave. With respect to incident wave, this reflected wave is 180 degrees, this is 180 degrees, right. These two are now in phase with each other, these reflected components are in phase with each other. You can see what happens to the other wave here. This goes into the second region, picks up a 90 degree phase shift, picks up 180 degree phase shift here, propagates back, picks up 90 degree phase shift, picks up one more 90 degree phase shift, and then comes out. What would be the phase of this one? Add up. 90 plus 90 is 180, 180 plus 180 is 360, plus 90 plus 90. So, this is basically 360 degrees plus 180 degrees. Again, the relative phase difference between these two is 2 pi. 2 pi phase difference is equivalent of 0 phase difference. So, all these three waves are now interfering constructively. you can then imagine that there will be one more wave which will also come back and interfere. So, given a certain broad wavelength band, and if I have designed this grating for lambda 0 wavelength, then the reflected wavelength will be at, or the reflected signal will be at lambda 0. Lambda 0 gets reflected, whereas all these other wavelengths get transmitted. Okay. So, this is the transmitted portion and this is the reflected spectrum. Of course, the reflected spectrum will not exactly look like this. Actually, if you take in dB, it would look like this. These are all the side lobes. Okay. This side lobes is coming because of the refractive index variation. This is in fact the Fourier transform of the refractive index profile. Okay. If you play around with the refractive index profile, then you can actually obtain a slightly better profile. Okay. You can reduce all these side lobes at the expense of increasing the main lobe width. Okay. This process is called as apodizing, or this is such a grating is called as apodized gratings. Okay. So, this is how a fiber Bragg grating works. There is one more device which is very important for amplifier situation. This is called as a long period grating. In the long period grating, you have the core propagation mode, okay, coupling to the cladding modes. So, cladding modes can be an infinite number of cladding modes, of which you have to pick a particular cladding mode. I mean, the construction actually determines all that picking stuff. So, if you look at the difference between these two, beta in the core and the pth cladding mode, and if this difference times lambda, which is the period of the grating, if this is equal to 2 pi or 2 m pi, then you are going to satisfy this constructive interference and the mode basically gets coupled into that. Okay. These are called as long period gratings, because if you look at the difference between core and cladding, this difference is actually quite small. In order to create a 2 pi phase shift, you have to make lambda to be very large. Okay. So, this long period grating has lambda in the order of about 150 to 200 micron. Remember, this is a period, the length of the grating is different. Okay. Whereas for the fiber Bragg grating, or the short fiber Bragg grating, which is implemented entirely in its core refractive index by changing the core refractive index, this lambda is about 0.5 micron. However, the width of the main lobe of the gratings is inversely proportional to the length of the grating. In order to obtain, say, around 1 nanometer lobe width, main lobe width, you have to take the grating length to be about a few millimeters. So, let us say around 10 millimeters or something. So, this is the length of the grating versus pitch of the grating. So, that has to be remembered. Pitch is the period. Okay. Period is 0.5 micron for a short fiber Bragg grating. So, this completes our discussion of WDM components. This can be implemented, I mean, these operations of filtering and multiplexing can also be implemented using thin layer films, thin layer optical films. You can also use what is called as arrayed waveguide gratings. These also have comparable performance with respect to the traditional things that we have discussed, but discussion of these components is kind of beyond the scope of this course. So, we will take leave here. We will stop discussing this passive WDM components in this module. Thank you very much.